So what we can do with a programmable timer, and remember I got my cameras. Now I got to figure out which one it is. Okay, there we go. So here's the programmable counter. And we have a little switch on the side. We call this a dip. I'm sorry. We have a slide switch right here where I can come up here and select what I want. A recycle timer, interval timer, a delay on make, we can put a retriggable one shot, a one shot, and a delay on break, which we'll talk about. And then once I set what type of timer I want it to be, then I come over here and then I set what we call a multiplier. If I can get this thing to focus in. So we set a multiplier. We can set it multiply by minutes, or we can set it to multiply by seconds. So right now we have it set to multiply by seconds. Then over here I got 0.1, I got 1 times 1, and I got times 10. Okay. So right now, if I have it on 1, and I have this set on 1, then the timer's going to time for 1 second. Right? And if I come up here and set this, it's going to time for 100 seconds. If I come over here and put it on 0.1, I'm going to take my little dip switch. By the way, don't ever use a pencil on these things. And why is that? Well, no, it's got graphite in it. Graphite is a conductor. So you'll get it inside your little dip switches and you'll mess up. So now I got it on 0.1. So this right here would be 10 seconds. And that would be 0.1 seconds. Or I could set it to minutes. So if I put it on minutes and put it on 0.1, that would be 100 milliseconds, right? You see that? So we literally can use this timer to time anything from 0.1 seconds all the way up to 1,000 minutes. So it's pretty good timer, right? A lot of your dashpot timers, you can't do that. If you want extremely long delays on a dashpot timer, you'd have one timer trigger another timer, right? This is pretty neat. PLCs, we don't have that problem. In a PLC, we just set up a timer and tell it what type of timer we want it, and then we just put a time out there. And we still put a multiplier. So most PLCs, you put a multiplier and then you put a time, which is pretty neat. So this is a programmable timer. And what does programmable mean? Doesn't necessarily mean that you're sitting at a computer writing a computer program. Programmable, which means you can change its function, right? Without changing hardware, basically. In the programmable timer we have. Retentive timers and non-retentive timers. We have what we call one shots. One shot. Normally, when you energize a timer, it'll stay energized as long as you have it power across the core. We have what we call a one shot. A one shot, what it'll do is that you energize the timer, and it'll give you one shot, and you set the duration of that one shot. Does that make sense? And it automatically goes, and we have what we call a non-retrievable. We have a retentive and a non-retentive. What would that be? This is something else. What is retentive and non-retentive? So this is in your book. They give us two diagrams right here. What does it look like? Yeah, so if we come up here and we de-energize the core, and then we bring it back on, it'll time from where it left off, right? Does that make sense? So that's a what? Retentive timer. A non-retentive timer would do what? Now you got to understand these are solid state timers. You say, well, how does it do that? Well, what we do on solid state timers, a lot of solid state timers is they don't operate if they don't have power. So normally some of our solid state timers are solid state devices, especially some of our solid state sensors, is we'll come over here and we'll have a line coming in here to the timer. And then we'll have a power lead that comes over here and goes to L2. So what this does is it gives us the ability to have these retentive timers. So if I wanted to energize the timer, then I would come over here, we're calling it CL2, right? CL1. So what this does is this does what? This actually powers up the electronics inside the timer. So a lot of your solid state timers or solid state devices, you have a power lead and you have to power up the solid state, right? You understand? So it's like your radio in your car. Does the radio in your car work? So what does the radio in your car do? Well, it takes these little signals coming in from the air and brings them into an amplifier and amplifies. Does your radio work when your car is turned off? When your switch is turned off? No, when there's no power on your radio. My radio does that too. So my radio, but when you remove power from the radio, does it work? Well, what's it doing? Well, so solid state devices have to have power to operate, especially if it's going to be an off delay timer, or if it's going to be a retentive timer, right? You understand? So when we say we're not removing power from the timer, we're removing the signal that tells it the time. Does that make sense? Yes or no? So I got a cycle timer. Well, most cycle timers would be a retentive timer because it's got a motor on it. So y'all seen our cycle timer? So this was a standard cycle timer for years. And so what we did is we had this little old cam. We had a synchronous motor down here at the bottom. So it would work kind of like the synchronous timer. Let's see where I'm at right now. So this is a cycle timer. This is an over cycle timer. And of course the way it's got is it's got a motor in it. And what I do to energize this thing, I put power across the motor. And then what does the motor do? Okay, I'm turning against the gears, by the way. It comes up here and turns. And what we're doing is we set a cycle, right? So this is the amount of time we want this thing to be on or off. I don't know. This is kind of a relative term because this is a single pole double throw contact right here. Okay. But when I turn this thing off, so I take power off the motor, and then I turn it back on, what's it going to do? It's going to take off from where it was at. Okay. So this would be an example of a retentive timer done manually. Okay. Now, solid state programmable timer, if it's a retentive timer, that means if we're going to de-energize the coil and we bring it back on, it don't start over, it remembers where it was at. Right? You understand? So that means that guy's going to have to be powered up. And that's where the make and break deal on this contact. So the solid state timer we've got, it's got a make and break. So what we're doing is we got two leads on there that we make or break, and then we can leave the timer energized all the time. That's a resistor. What size is that? Brown, green, red. Huh? 1.5. Okay. An on delay timer. So this is an on. So notice this is the symbol. There was a bunch of y'all that messed up on your lab. So you had questions back and it says draw a circuit that hooked push buttons in AND configuration. So y'all come up here and you did this right here. That's wrong. Why is that wrong? That is not the symbol for a push button. That is the symbol for a relay contact. And it's very, very important that you understand symbols. Somebody said, well, this is what I used in a PLC. No. This is what you use to simulate it. If you look at the connection of a PLC, when you connect it up to the ports, they would use the symbol for a push button. It's just that push button is simulated in the PLC as a contact, right? You understand. But when you look at how to wire the PLC up, they have to use the right symbols for the devices that they hook up to those inputs. So if you did this, then you were wrong. And using the right symbol is important in our trade, because if you use the wrong symbol, you could get somebody killed. Because they're expecting one thing and you put another one in there. So this is why we had y'all memorize those symbols. And we didn't have you memorize them so you could just throw anything in there you want to. So if it says in there to put 3 push buttons in parallel, then that is not 3 contacts in parallel, right? Y'all understand that? That is a symbol for those for push buttons. And some of y'all did that. How do we hook? And some of y'all did this too. And I hate to preach at y'all. But I just don't want you to get out there and get yourself or get somebody else killed. So I saw this kind of stuff right here, and I want y'all to explain this to me. Every circuit has got to have a load. You cannot short out the load or you have a short circuit. So maybe you'll say, well, I'm going to do that. Something about use a float switch to control a circuit. And this is what somebody did. They come over here, and like they came over here and they put a float switch right here. Normally opens, by the way, go down. They put a float switch. They came over here and did this, L1, L2. What happens if that float switch closes? You have a short circuit. Somebody came over and did this. It said something like add a push button to turn the light on. They come over and put a push button in parallel with the load. So what happens when you press that button? Short circuit, right? Y'all understand that. I had more than one person do here. They say turn on a horn. They said turn on a horn. So they come over and use the symbol for a horn and turn on a red light. I had more than one person do that. What's the problem with that? How many loads in a line? 1. So we teach all this stuff, and then you go in, when they ask you to do it, then you just basically, I don't know what's going on. This is homework. These are on your homework labs. So I don't know what to tell y'all. Of course, you lost all the points for that, even if you use the right symbols. If you got a short circuit, I can't give you the full points for that circuit, right? So this is the symbol for the contact of an on-delay timer. So an on-delay timer, the timing occurs when we put power to the symbol of the timer relay. And it might not be actually a relay, it might be electronic, right? You understand that? So on-delay timers would be like this guy. So this is an on-delay timer. So when I put power across the symbol of the coil, which would be up here called TR, then this thing's going to start. Okay. So notice here, here's the flat part of my armature, and when I come up here and energize this coil, can you see the dash pot working now? Okay. Speed it up some. Increase time, decrease time. God gracious. So we come up here. So when does the timing occur? When I put power across the timer symbol, right? You understand? So this would be, this guy here, it's got 4 contacts on it. One of them's normally open, one of them's normally closed. So the normally closed would go across here. The normally open would do what? Go right here. So the timing occurs when we energize the coil, or the symbol for the coil. We still use this same symbol, whether it's solid state or not. We still use that circle, because that's not a control device. It's not a symbol. So anytime we're going to have something that controls contacts, we're going to use that round circle up there. This is a normally open time. So we would call this a normally open. The nomenclature for this is a normally open timed close. So we'd come over here, normally closed is going to go across the top. We're going to come up here and open that up. And we would call this what? Normally closed, timed open contact. So what happens, I come up here and let's say we got the timer set for 10 seconds. And I come over here and this switch right here closes. Is this switch right here going to close at the same time we put power across the timer coil? No. It's normally open, timed close. So this guy right here would close after 10 seconds. This guy right here would open after 10 seconds. Of course, the second load would never come on, but I wanted to show y'all these 2 contacts, right? So here we come over here, we put power on the coil. See, load off, timer off, load off, timer on. So here's when we put power across the coil. After the time, then that light would come on because I'm using a normally open timed close. So on your own delay timers, the contacts are opposite. So if it's normally open, it's going to time closed. If it's normally closed, it's going to time open. So let's say I come over and open up this switch. Well, the time is not on energized. The time is not on de-energized. The time is on what? Energized. So this contact right here would open instantly, and this contact right here would close instantly. So when I de-energize the timer, they go back instantly, right? You understand that? When I energize the timer, so if I look at this guy right here, so I'm going to push my armature down. You can see the little dash pot. When I let it go, it pushes it up instantly, right? You understand that? So the dash pot, so we have what we call a check valve. A check valve only lets the fluid flow in one direction. So when it's coming down, it's having to go through the dash pot or orifice. When it goes back up, when we push it the other way, it opens up the check valve and lets it go through with no time at all. So this right here is an on delay timer. We have 2 contacts. We have this guy right here, which would be a normally closed time open, and as soon as my focus comes back in there, and the bottom one is a normally open time closed.
So would you say that's non-retentive because it resets instantly?
Yeah, because as soon as this is non-retentive. So what happens on this one, if power fails, that sucker goes right back up there. So that means what would happen is that when I energize it again, it would start from scratch. I guess I passed my off delay around. So if you see the symbol, if it points toward the contact, Then this right here is an on delay. Makes sense, right? If we take that same symbol and draw it like this, then we have a what? We have an off delay. So if the arrow points away, it's off. If the arrow points up or toward the contact, it's on delay. So it says the contact's open, but this is only has one set of contacts. So this is the symbol here. Okay, so this is a normally what? Normally closed, timed open. In your book, it looks like I came here and cut the face of this, so y'all probably need to look at this one. I don't know what figure this is and see if they got the right symbol. So can you see the little white there? It looks like I cut and pasted the symbol. Is it right? I don't know what figure this is.
Figure 1410.
So this is basically the way, this is not quite, they don't show you the check valve on there, but this is what, so we have two cavities in there. And then of course what happens, we have an orifice, and then what do we do with that little dial? We control the size of the orifice. So with an on delay timed open function, the contact's open after the timing cycle is complete. So on an on delay, you energize your timer, and then the contact switch after a time, right? You understand that? Yes or no? This would be like I want a stagger start motor. I would use an on delay timer. So what I would do is I would come over here and so this would be a stagger start situation. And we do this a lot where they start motors in sequence and not at the same time. So up here I might have okay. So up here I might have a standard start-stop station or a 3-wire control, right? And then we'll go ahead and make this an M. Don't forget your dots. How many forgot their dots? Cost you 2 points. And then I would come over here, and this would be M. This is the motor starter, and I would put a timer right there. But I'd do an on delay timer. And down here on my second motor, if the contact could run the motor starter, then I'd come over here and I would do a what? I use a normally open on delay, and then I'd come over here and I'd put M2. So we can hook loads in parallel, but we can't hook them in what? Series. Y'all understand that, because like I said, more than one person did that. We had one person that put a circle and labeled it horn. And that's not the symbol of a horn, that's the symbol of a what? Relay coil. So you should have went back in your book and looked for the symbol of a horn. An off delay timer, or some people call it, they say delay on release, but I've never heard of that. Off delay timer is a device that does not start its timing function until the power is removed from the timer, or the power is removed from the timer of the coil. So this might be a solid state timer, and you might see this. Why would you say that? Because it's solid state. Radios don't work if you don't have power to them. Solid states don't work unless you have power to them. So you might have a third lead that goes to L2. But when we talk about that third lead going L2, when this says remove the power, they're talking about across here. In fact, this is not quite right either. We have to do something else. Just take this a little down. Normally when we do this, it has to be what we call a contact control timer. So we have to put the timer all the way across that one and up to each other. So this is an off-delay timer. So what happens, now notice what they did, so what would this be a symbol for? This is a normally open, timed open. So on off delay, they're the same thing. On delay, it'd be normally open, time, close. It'd be normally close, time, open. On an off delay timer, they're the same. Because I come over here and close this switch, it does not time when I de-energize it, it times when I de-energize it. So I close that switch, I put power across my car, this contact closes instantly. Because the time is not closing, the time is opening, right? You understand? I come up here and open this switch. We have our timer set for 10 seconds. Well, this guy's going to continue to run for 10 seconds. So it's like my heater. So my heater comes on, it cuts off, and my blower motor runs for a little time before what? Before it cuts off. My light stays on a little while after I get out of the car. My dome lights come on when I open the door, but when the door is closed, they don't go off instantly, unless I turn the ignition on. So if I'm getting out of my car and I pull my key out and I open my doors and I close them, then, right? So I go out there and unlock my doors, my lights come on, but they don't stay on. So if I don't go out there and climb in my car after a certain amount of time, what is it? They automatically cut off. But my dome lights actually dim, so they don't go off instantly. Most cars do that. So there's a little more to it, but you understand these timing things. So we run coolers all the time. So you know, even some cars do that. So a lot of our cars now, used to in the old days, the radiator was driven by a fan that ran off the motor. A lot of your cars now are front-wheel drive. My car's front-wheel drive. Well, what do we use to blow air through the radiator? We use an electric fan. Have you ever got out of your car, open the hood, and that fan's still running? So they actually keep cooling that thing down for a certain amount of time, right? When I turn this projector off, the fan still runs. Because they don't want the bulb to cool down real fast. They want it to cool down, right? You understand? Or a control cool is what they want to do. So those are the examples of off delay time. We have a timer. Usually, if you got a compressor, we don't like to try to start compressors up under load. They'll stall out and burn off. So I got at my house, the power fails at my house and comes back on instantly. The compressor don't kick back on because it's got an on delay timer on it, right? You understand? So a lot of y'all see that. You even on your thermostat, you turn it on and it takes a little while for the compressor kicks back on because it's got to go through that on delay timing cycle. So this is a normally open, timed open. And then of course this would be the symbol for normally closed. I'm going to come up here, I'm going to point the arrow away. This would be a normally closed, timed closed. Because it doesn't time when you energize it, it times when you de-energize it. So that means a normally closed contact, when you turned it on, it opened up instantly. And then what would happen when you turned it off, then after a certain amount of time, it would close back. So these are off delay timers.
Can you say that again?
So what I'm going to do is I'm going to come up here and change the symbol. So what I'll do is I'll just mark through this one. So I'm going to come over here right here, so we're not going to use that at all, and I'm going to change the symbol over to a normally closed timed close. And I got that light. So right now the light would be on. Right, you understand? Okay, I come over and close that switch, the light goes off instantly. Because it's an off delay timer. It's not an on delay timer. It's an off delay timer. So when I energize the coil, that's not turning it off, right? That's turning it on. But the time is not. So this, understand. So this guy would open instantly. Okay.
Normally close timed open?
What's that?
Normally close timed open?
It's a normally closed, timed closed. Okay, so I turn my switch on. Okay. Oh, I'm sorry. Thank you. You said I used the wrong symbol. That would have made sense. You should have said you're using the wrong symbol. Yeah. Okay. Because we're talking about off delay timers. So I was just doing that to make sure y'all paying attention. So Kyle was on and paying attention. So what would happen? I close the switch. The timer does what? Yeah, it opens instantly. I can understand the confusion now. And then when I open the switch, then after 10 seconds, so the light would stay off. After 10 seconds, it would turn back on. Thank you, Kyle. In fact, that's still not the symbol. So the symbol is not a filled in arrowhead, it's what? Yeah, like. An off-delay timer contact circuits may be used to provide cooling in a projector once the bulb has been turned off, but has not had time to cool down. Of course, this is all built into the electronics. These guys have been around so long. And what happens, if you got the same device, it does the same thing over and over and over again. Sooner or later, somebody's going to integrate that into one IC. It's just like in the old days when you looked at a video card, it had hundreds of ICs on it. And now you go out and video cards got one IC on that because all of them do the same thing. So they used to have memory on it. You can see the memory on the card. You can see everything on the card. And now, then they went to a video processor, and then they integrated the memory into the one IC. So if you now your video cards are integrated into your laptop or your cell phone. So now you get what you got. In the old days, it used to be nice because you could upgrade your video card, or you could run multiple video cards, which was really neat.
You still do that, just cost on money.
Not in a laptop. You can do it on a, I don't know, I guess you could.
There's a couple of laptops.
The desktops you could, as long as you got the slots, you could put.
Usually just upgrade from RAM in your laptop.
Yeah, but you cannot, well, but the video cards we use now share the RAM with us. So this is a normally closed.
Normally closed, time closed.
Normally closed, time closed. So your on delay timers, they're just opposite. So we'd have a normally open, time closed. We'd have a normally closed, timed open. On your off delays, they're the same. Normally closed, time closed. Normally open, timed open. So this would be a normally closed, time closed. So right now my timer would be energized. If the timer's energized, then it's going to come up here and open this guy up here up. Right? So this is the position it would be sitting in now. When the pressure switch comes up and builds up, then what is it going to do? It's going to open it up, and then after a certain amount of time it's going to close this and turn on this pump motor. The off-delay timer contact circuit may be used to provide a pumping system when backspin protection and surge protection on stopping. I don't know how that's going to do that. So here we got this symbol right here. Here's your symbol. We're adding symbols. This is the symbol for the contact, not for the timer coil. The timer coil, even though it's solid state, we still use that circle because that's our outlet box, right? And that, even if it's solid state, it's still controlling contact. Everybody understand that? So that circle is the symbol I use in a motor control for a timer. I'm not sure what Siemens use, but on a PLC, the timer is actually a square block because you got so much information you got to put into it. If you take PLCs. But we have on delay, we have off delay, we have one shots, and of course that's programmable. So normally open, time, close. So that's an on delay timer. Normally close, timed open. That's an on delay timer. Normally open, timed open is a off delay timer. Normally close, timed close, an off delay timer. And of course these are just our what? And untimed contacts. This gets a little confusing in PLC because these are the same contacts you use for your timers. And timers are internal. A one-shot interval timer has contacts which change positions and remains changed for a set period of time after the timer has been received power. So these are one-shots. So if we energize the timer, and no matter how long I take to energize the timer, this guy here is going to energize. It's going to come over here or change conditions. Now, these guys just show light on, so they're using a set of normally open contacts. And then automatically after that time, it's going to do what? It's going to return to its off state. In digital, we call this a monostable multivibrator, so it's got a big name to it. That's the technical name, but we call them one-shots. We use these things for, we'll talk about that in a minute. So to get another shot out, what would I have to do? I'd open the switch, and then when I close it, right, you understand. Yeah, to get another shot. That's why it's called a what? Now we have two categories of this. We have what we call, let's see if they talk about it. We have what we call a retriggerable and a non-retriggerable. So a non-retriggerable, so let's say a one-shot, how would this work? Let's say I come over here and I close it. Let's say this is 15 seconds. And then I open it up before 15 seconds. Yeah, it's still going to go. It's still going to give you this one shot. Okay. Y'all understand that? Now, then we have what we call a non-retriggable and a retriggable. A non-retriggable would give you 15 seconds no matter what. A retriggable means you get 15 seconds from the last true. Does that make sense? So if I had a retriggerable one shot, that means if I come over here on a one shot and I open the switch up, it's going to give me 15 seconds. I could close that switch 100 times, so I could open and close it 100 times, and it's still going to give me what? 15 seconds from the first trigger. A retriggable is going to give you 15 seconds from the last contact closure. So it means I come up here and I open it, and then I close it, it's going to time 15 seconds from the last time it was closed. And we call those retriggerable one-shots. We use those things for like what we call missing pulse detectors. When you're looking for a string of things happening and all of a sudden they don't happen anymore. Well, as long as that thing's coming by there, so let's say I got a manufacturing line and I got these guys coming by there, and every time it goes by a sensor, let's say it goes through a through-the-beam sensor, and every time it comes back here, it re-triggers that thing. And then all of a sudden the can stop coming, right? You understand? Well, what would happen if we don't re-trigger it, then it would time out, but it would still give it a certain amount of time. These guys are used a lot. Some people call them missing pulse detectors, but these are what we call re-triggerable one-shots. So a non-retriggerable one-shot does what?
It gives you the set time.
Yeah, so I come up here, I close the switch, I open it, it's going to give me 15 seconds. I close the switch before the 15 seconds is over. I open it, it's still going to give me 15 seconds from the initial trigger. Okay, that's a non-retriggerable one-shot.
So you're saying it don't reset?
It don't reset. A retriggerable one-shot resets every time. So it means what? So a non-retriggerable time, it triggers from the first closure. A retriggerable retriggers from the last closure, right? You understand? So we retrigger it from every time it closes. So a non-retriggerable, I can sit there and flip that little switch from now to then today, and as long as I do all those switch closures within 15 seconds, it's going to still work. It's going to time for 15
So
seconds.
you would have to wait until those 15 seconds are over.
If you wanted to trigger it. Yeah. A retriggerable though, it's going to trigger from the last. It's ongoing. Yeah. As long as you re-trigger that thing before it times out, it would time forever. And that's why we say some people call these missing pulse or missing parts detectors. So we got these parts coming down on the line, and these guys are extremely fast. And we need to know if something happens and we have a jam. So these parts are coming down there wide open, and we need to know right off the bat if the parts are not coming down there anymore, right? So what happens is we take these things through the beam detector, and they're flying through there, and all of a sudden they stop, and we got it set for 10 seconds. Well, if we don't get parts moving again within 10 seconds, then we sound alarms and shut the lines down before we really cause some problems. So that's one shot. So this is a type of timer, a recyclable timer. Y'all okay on that? Yeah. So this is a cycle timer or recyclable timer, and we have the ability to do that on our programmable timer. We can set up a cycle timer, a recyclable timer, and then we set the amount of time between the cycles. So I'm out there and I want my yellow light to blink off and on. Well, if you got a caution light out there, just do it more. Well, what's it use? Yeah, it's using a cycle timer. That's exactly what it's using. Okay, guys, y'all take a break. Nobody raised. Nobody did that. Oops. Some people just call it a cycle timer. That's what it's called on our.
Unit is right here.
Yeah. I forgot to put this one up there. This timer right here is pretty unique in that it's both an on delay and an off delay timer. So notice it has two dash pots. It has a dash pot on both sides. So what happens is when I pull it in, this is an on delay timer. This is an off delay timer, which is pretty neat. So this has both an on delay timer and off delay timer on both sides. So this is my off delay timer over here. Here's my on delay. So this closed instantly. Now this guy here's timing. So this is on delay. Now notice when I let it go, this drops in instantly, right? So it changes states instantly. Now this right here is timing. So I like this timer. It's pretty neat.
What have you used for?
I mean, that's a perfectly good question right there.
Yeah.
It's a good question, Kyle, but I don't know. Multiple function timers may be used to place the switches. So ours is a programmable typer. This is what the book is referring to as a multi-function timer. May use the placement of dip switches. Trying to look. I should have brought some over. No. But when they started integrating circuits in IC, so what we used to do is we had what we call discrete components, which means the circuits were made out of individual components. Over time, they realized that a lot of times we didn't need a lot of current drive, so they could make the components a lot smaller, and they could integrate an entire circuit on a single little IC or a chip. And these became known as integrated circuits. One of the first packages they put these in was what we call a package that from the top. And of course, this is going to be a lot bigger. And then we had a notch that indicate which direction it went in. And then on the side, they had these pins. If I was looking at this from the side, we'd see they would curl out and they would come down, and then they'd loop in and they'd come into these nice sharp pins down here. And what we call this 1, 2, 3, 4, 5, 6, 7, and they run in groups of twos. And we refer to this as a dual inline package. And it became an acronym of DIP. Well, the spacing between these pins and the size of the chip became so popular that people started making sockets that we could come in and we could plug these things in and take them out. So when they started making these little old tiny switches, they made them in the exact dimensions of these guys. So they might put 4 switches inside there, but they were still using the exact same width and the same space in between the pins. And so this is why these things started. We started calling them what? Dip switches. So that's how they got that name, because they're in the same size. So that means when I'm trying to set up my mask for my printed circuit board and I want to put these little switches on there, I could just use the mask for an 8-pin dip and put it in there and then plug the switches in there, right? You understand? So these are very, very popular. So on the front of our programmable timer, where's it at? We have a set of dip switches. And like I said, no, that's not the programmable timer. Where's the programmable timer? Yeah, so we have these set of dip switches, and you'll run into these a lot. And like I said, don't switch them with a pencil, right? You can switch them with an ink pen, that's fine, or you can switch them with a paper clip, that's fine, or a small screwdriver, that's fine. But don't switch them with a pencil. And why is that? Because the graphite will get into it and mess it up eventually. And then this right here is a multi-position slide switch. So this is what we use right here to program what type of timer we want. So there's a recycle timer. Here's an interval timer. Here's a delay on make. Here's a delay. Here's a retriggable one shot, or they're called in a single shot. Here is a single shot, so that would be the non-retriggable. And then we can set it on delay on break. So delay on make would be a on delay timer. Delay on break would be an off delay timer, or simulating an off delay timer. That makes sense? So I've got this one guy right here. This is a universal time relay that in my plant, instead of me trying to buy all these off delay timers, on delay timers, run shots, and all that other kind of stuff, I got one relay, or one timer that I can do what? I can program it to whatever I want, and I don't have to worry about that, all these spare parts and stuff right there. So I got 15 timers out there instead of having 50, and they're all different. Instead of having 15 spare parts, I might carry 2. Right? You understand? And just think about how much money in the long run that would save us. We got the data sheets on this thing, by the way, and it's up on the. What's nice about this guy is that when you look at the data sheets, so here they don't call it the coil. As soon as it zooms in, they call it input. This is your input power. And when we look at the data sheet, we can put DC or AC on this thing. So that means if you bring AC in, they rectify it and turn it into DC. So this powers up the timer. And then what we do to make it start timing or not timing, we have another set of contacts, and it's still not focusing on me. They call it over here on the side, they call it what? Initiate switch. So this is where we put when we want our timing to start. So I would put a set of contacts right here, and then I might set it up for delay on make. So that would sit, so when I energize the other coil, this guy would start timing. Or if I set it up on delay on break, then I would have a control relay, and when the control relay broke those contacts, it would start timing. So what we would do on this guy is on there that we use to configure things. Then what we would probably do is what? We would come over here and we hook the timer up across L1 and L2 all the time. All the time. And then we would come up here and we would, if we call this TR1, and then we would come over here and we'd have a relay, you know, that we might push a button or whatever. And this might be CR, and then we would set a set of CR contacts right there. So this is the way we would draw that. And this would be between that initiate. So if I set it up on delay on make, and this closes, CR comes in, this right here closes, and it would start timing. So this is going to simulate an on delay timer, right? And then if I set it up for time on break, when CR de-energized, it would open those contacts and then it would start timing. So what it means is I would have to use this guy to make this thing work as a timer. I would have to use it in conjunction with a control relay. But I could do this on every one of my circuits, right? Does that make sense? And so that's what's so nice about this guy, which is pretty neat. So that's what the delay on break and the delay on make means. So let's see what else we got here. I think this is probably all we're going to. Multiple function timers. So this is what they're talking about, the supply voltage timer. So this is what we call a supply voltage timer. So we have a voltage control timer and a supply voltage timer. So a voltage control timer controls when we put power across the coil. The contact, so let's rephrase that. So supply voltage timer, these are voltage control timers. These start timing when we put a voltage across the coil. A contact control timer starts timing by the position of a set of contacts. That makes sense? So our programmable timer would be what we call a contact control timer. But we don't have to use it that way if we're using it for an on delay timer. So if we're using it as an on delay, even though it's contact control, so this is what we'll have to do. Where's mine? I need a blank page. Oh, I can do it down here. So if we was going to use it as an on delay timer, then what we can do is we just jump the initiate. We just put a piece of wire across that. And we set it for time on make. So that means if I come over here and pushes that button, and this is across that initiate, I put power on the timer, we say time on make, well, it's going to be what? It's going to be made. So if we're going to use this guy as an on delay timer, this is what we do. But we'd set it up to do what? Time on make. You understand? Yes or no? Okay, so we got what we call a contact control timer. But it's got solid state. So as soon as I put power on the solid state, then that timer's going to start working. I have it set on time on make. Well, I got the two dang wires jumped together. So do I have a circuit between the time on the initiate switch? Well, yeah, because I got it what? Jumped out. So this is the way I'd use this guy as an on delay timer. I would program it to time on make, right? You understand? And then I just jump out the initiate switch. And now it's an on delay timer. Make sense? Now let's say I want to set it up for an off delay timer. Well, if I remove power from the solid state guy, it is not going to time, right? You understand? So to use this as a solid state timer, I'm going to have to use this, a solid state off delay timer, I'm going to have to use it in conjunction with a control relay. Okay, then I would come over here and I would take my timer and I would put it between L1 or CL1, or here would be my timer core right here. CL2. But then I would come up here right here and I would go between my initiate and I would put a CR contact with that. But then we would tell the program to time on break. So it's not the on delay. The on delay has no problem, right? You understand? So this would be like me turning on the radio, right? You understand that? Okay, so as soon as I put power on the timer and we got it set on time on make, then it's going to work fine. It's that off delay timer on a solid state timer that we got problems with, because if I pull timer off, if I turn the power off the solid state timer, it's not going to work. It's not going to work. Y'all understand that? So off delay, we have to power the timer all the time, and we put a set of contacts. So off delay, we use this thing in conjunction with a control relay. This is what we call a contact control timer. Now a voltage control timer, which is like what this guy is right here. So this is the contact control timer, but we're still, it appears to be a voltage control timer. So this is, where's those timers? This is a solid state timer right here, but it's an on delay timer. So that means I have no problem on this on delay timer because it's electronic. I put power on it, that turns the electronics on, and then it'll start timing, right? You understand? So this would be what we call a voltage control timer. Y'all understand the difference between the two? Between a contact control timer and a voltage control timer. Most programmable timers are going to, if we're going to put a solid state timer and we're going to use it as an off delay, we're going to be, right, you understand, that would be like trying to listen to your radio when it don't have any power. Can you listen to your radio when it has no power? No. So solid state devices don't work without power, right? You understand? So this is when we use the actual true contact to control it, not as an on delay timer, but as a off delay timer. And this will be our program. And of course we would use the contacts. We would still use the same contact symbols that we use. Another thing that some of y'all guys are really, really having problems with is reading these dang timing charts. I don't know why. I guess I've been dealing with these things so long, I have no problems. So y'all had all kind of problems trying to do those timing charts on the ands and the ors. So they got over here and they said input 1. They said input 2. And then they drew a line over here, and then they made them go true, and then they made them go false, and they made them go true, and false, and true, and false. And then they came on one down here, and they came over here and did something like this. And this would be on input 2. And then down here they had the output. And then they come over here and put something like this. And they wanted to know what type of logic that is. And this is what we call a timing chart. To me, this shows out exactly how it works. What logic is this? Well, if I look at my 2 inputs, the only time the output is true is when input 1 and 2 are true. So this would be a what? That would be an AND. I don't know why people have so much problem with that. Now I could come over here and take those same diagrams and come over here and do this. Now the output is true when input 1 or 2 is true, so this would be a what? That would be an OR. And we get the same thing on timers and stuff like that. We call them timing diagrams. And these basically show how the output responds to your inputs. And man, in digital, we use these things all the time. And then they had one that had one input. It had input, had one input, and then they came over and did this, and the output was just opposite of that. So what did that have to be? That had to be a NOT, right? So let's see how we're doing. Let's see what we're doing. Let's see. So we'll recycle timer, dip switch, multi-programmable timer, supplied voltage timer. We're going to call this a voltage control timer, contact control timer. So a contact control timer is going to be set up with a contact. On delay, we have no problems. We just jump the contacts. Off delay is where you got to add that controller, or add another device that's controlling the timer. Transistor control timer is controlled by an external transistor from a separate power source. And seen these, but all this is just a contact control timer, but they're switching the contact with a transistor. So a transistor is like a valve. It's a current valve. And we have 3 leads on it. We have what we call a base, emitter, and collector. The collector, the emitter's got the arrow. The collector is this guy right here. And what we're doing is we're controlling the current flow between these 2 leads right here. And we're then doing it with a 3rd lead that we refer to as the base. And I got those names right. So what can we do with a water valve? What do we do with water valves? What do we do with water valves? Well, we can run. Some of them run in 2 states. We call them off and on. That's what digital is. So we either turn the transistor on or we'll turn it off to the base. Or we can run it in what we call the active region. And if you're familiar with electronics, that acts like a rheostat. Which means depending on how much base current we put onto will depend on how much resistance we have between the connectors. So the amplifiers. So stereo amplifiers operate the same thing in the active region. Because that would be awful if the music was nothing but on or off, right? All you'd get was a bunch of clicking sounds. So we don't hear clicking sounds, we hear voices. And voices are analog. Okay, so what we're doing with the transistor, well, what we're doing is we're using a real small base current to control a real big collector to emitter. So it's like, I could go home and I could turn a faucet on and I can try to stop the flow of water with my hand. Can I do that? But I can take that little tiny knob up there and I can turn it real easy, and I can control the flow. I can turn it wide open, or I can turn it all the way off, or I can do it in between. Well, what it is you get a mechanical advantage. Anybody ever had one apart? You got a worm gear in there, and the slope of the worm gear and the number of threads depends on what type of mechanical advantage you get. So it's because of that valve, that control valve, that allows you to control the flow of water. And that's what the base does. The transistor, we're not controlling the flow of water, we're controlling the flow of water. Current. Bipolar transistors use a current to control the current. Field effect transistors, or FETs, use a voltage to control the current. So that's basically, the FET calls them gate, which is similar to the base, and drain, which is similar to the source. Drain, which is similar to the collector, and then the source, which is similar to the emitter. They're not the same. They're two different devices. So I can use a transistor as a switch. Thank God. If I can use a transistor as a switch, and I was doing relay logic. Now, I know how we do ands and ors and stuff like that. Now I can do that same logic with a transistor. A transistor, we're not dealing with a lot of current. We're dealing with, so I can take logic circuits, ands, ors, nots, and nors, and I can put thousands, or millions or billions of transistors on a 1/4-inch wafer. So I need to know, I need to look that up. An i7 processor, see if I find, look that sucker up and find out the equivalent transistors that thing has inside of it. And how do they do that? Well, they're not controlling a lot of power. All they're doing is providing ones and zeros. And it's just like any water valve, you know, how much water it controls depends on the size of the valves, right? You understand that? The less water we have to control, the less force we have to control, the smaller the valve can be. And that's the same thing true. So if all we're doing is giving ones and zeros, we can make them extremely small. So we can switch that thing with transistors. We could switch it with transistors. It would have to be a DC switch, though. We have what we call triacs, which are AC switches, which are pretty neat. So proximity switchers, we could use a proximity switch to switch the timer. You know, we could use, I don't know, all this stuff is just kind of garbage. It's pretty neat, though. Billion. Right, not million, billion. And the problem is they got a bunch of memory. They got what they call caches in there. It's really interesting the way they work now. Then they can do multiple cores. How many cores? i7. How many cores does it have in there? Still, we aren't running 2. Of course, I don't know what a core is. There's one more thing I needed to touch on. We're going to try to wire this up. For years and years and years, what advantage does a DC motor have over an AC motor? Well, all types of controls. So especially if it's a separate excited motor, what I can do is if I increase the current to the field, the motor slows down, but it creates more torque. If I decrease the current to the field, the motor speeds up and creates less torque. So using the field, I can control the torque. So that means if I raise the voltage on the armature and raise the voltage on the field, not only do I get the same speed, but I get more torque at the same speed, right? And so the big advantage of an AC motor, a DC motor, is that we can control the characteristics of the motor a lot better. And for years and years and years, the big advantage of DC is we can control it electronically. So this means for years, variable speed drives were DC. They were DC drives. And that's because we wanted to control the power getting to the motor, which means we needed DC. The problem we have with AC motors is that if we increase the voltage above its rated value, the motor's not going to run any faster. Y'all understand that? If we decrease the voltage below its rated value, it's not going to generate the horsepower that it needs. So you could very easily, so it will slow down because it's got to create more, try to create more torque. But if you drop it down too much, it's going to stop. Okay. So normally we do not control the speed of most AC motors with changing the voltage. The only place I know of is on some fans. Because fans, the slower they run, the less torque they need, right? You understand? So a fan creates all its horsepower when you're running it wide open. So a fan hardly needs no horsepower at all to start it. So that's why we usually use split phase motors. So how do we control the speed of an AC motor? RPM of the field is equal to what? 120 times the what? Frequency. And why we're using 120? Because our speed is in RPM, and M is a minute. So if I used pole pairs, so it makes one revolution per pair, so that'd be 60, right? You understand? But we're using poles, so that's why 120 came. So what we're doing is we're taking revolutions per second. So if you take the frequency and divide it by the poles, you get the revolutions per second. And then we multiply it by 60 to get the revolutions per minute. So 120 times the applied frequency divided by what? The number of poles. So how can I control the speed of the motor? Now we'll always, if it's an induction motor, we always have slip, right? So the speed of our rotor is going to be slower than this. So how can I control the speed of an AC motor with not having it stall? We don't use, huh? Yeah, but we can't do the frequency. Can't do the frequency by itself. One of the normal ways is to control the number of poles. So we change the number of poles. So that's when we look at this. That's when we look at this motor right here. Why do I have a back door? So when we look at this motor right here, this is a 3-speed motor. Capacitive motor. So why do we have all these wires coming out of this thing?
Control which number of poles.
Because you control the number of poles. This is a pretty standard color code. So this says blue is high, black is high, blue is medium, and red is low. There's where you start the capacitor goes, right here. Okay. And then here's red. So red would be what? This is low. Then blue would be medium. And then black would be high. And then yellow is common. So what we do is when we switch to these different wires, what are they doing? They're changing. How are they changing? They're changing the number of poles. If you took the switch, if you got a ceiling fan in your house and you took that speed control on there, it would have 3 wires coming out of it. One of them's for medium, one of them's for low, one of them's medium, one of them's high. What are you doing when you flip that switch? You're changing the number of poles. But these guys,
that's why they have 3 speeds.
3 speeds. Normally we don't use this. Most houses use just 2 speeds. We run it on medium speed for heat and slow speed for cold. Because we got to move more air volume when we're running heat because the air molecules are all spread out.
That's why our AC fan is so loud and rewire. Sometimes
you can do it. Sometimes you can jump It's not very hard to do. If you wanted to blow harder, what you would do is just go to medium and high instead of low and medium.
It didn't help it. It's like that to the wall, so it's gonna be loud regardless. I thought they maybe set it too high.
Okay, so the problem we have with, and then the two brown wires, this is where it's the frequency, is we can't just control the frequency. Because we have this big thing, so a coil is made out of an inductor. And the opposition that the motor represents, we call it X of L, is equal to 2 pi L. Now this is a constant, and we don't change the L of the motor. The L of the motor is the number of windings you have, what type of metal, right? We call that the L of the inductor. 2 pi is 6.28. We don't change that. The problem is if I change the frequency. If I increase the frequency to cause the motor to run faster, it's going to offer more opposition. It's going to stall on us, right? You understand? If I drop it down, the dang thing's going to start. It's going to slow down, but now all of a sudden it's going to pull a lot more current. It's going to become very, very, very inefficient, right? You understand? So normally what we have to do is people call them variable frequency drives. I call them variable speed drives because what that guy has got to do is not only does it change the frequency of the motor, it changes the voltage to the motor. So when we program a variable frequency drive, we basically enter all that nameplate information on there. And two things that we enter is the voltage that the motor runs and the frequency it runs at. So let's say it's a 120 volt motor. Okay. At 60 hertz, 120 volts. So that's what the motor's rated at. But what I would do is we come up with what we call volts per hertz. So what would my volts per hertz be? 2. So that means if I put 2 volts on that thing and 2 hertz, it would pull exactly the same current that it would pull at full load. If I put 4 volts at 4 hertz, the motor would speed up, right? You understand, and run exactly the same horsepower. If I put 6 volts and 6 hertz, so as long as I maintain that voltage to hertz ratio, and we can control the speed of this motor. So what they do, what a variable speed drive does, it don't only change the frequency, it has to do what? Change the voltage. So if the frequency goes up, the voltage gets higher. If the frequency goes down, the voltage gets lower. As long as it maintains that voltage to the voltage per hertz ratio, these guys will run forever. But we have problems starting with these low frequencies, right? So normally what these guys will do to start the motor, they'll flip it across the line, let it do what? Let it start, and then it'll switch into this frequency. Very few of them unless you run them down to nothing. I think our variable frequency drive is like 20 hertz. I think we go down to 20 hertz. And then after that, you can't go any slower than that. Yes, but they don't control. But we're talking about what advantage does DC have over AC? So your car stereo, the speakers on your car are AC. If you put DC on the speakers of your car, it would burn them suckers up just like that because they have no resistance. We call them 8-ohm speakers, but that 8 ohms at 1,000 hertz. So if you put an ohm meter across the speaker and it's an 8-ohm speaker, it's going to measure a lot less than that. It's going to measure less than that. Okay, it might measure 6 ohms. So if I put DC across, if I put 13 volts across 6 ohms, how much current will we have? Okay, it's not that much, but it'd burn them up, right? You understand? Okay, so we don't put DC on our speakers, we put AC on our speakers. Well, how can I go from DC to AC? Well, it's electronics and it's DC. What can I do with electronics and DC? By George, I can do just about anything I want to, right? So I can take DC and turn it into AC. Well, when I take DC and electronically turn it into AC, what can I do? Well, I'm not dealing with Alabama Power anymore. I'm dealing with my electronic circuit. Right? You understand? So now I can play music at all. DC has no frequency to it, but I can run that through my amplifier inside my radio. What does it do? It's taking DC and converting it to AC. But the AC is varying with the what? With the music. So it's pretty easy. All we do is we just take DC and we generate two voltages. To get AC, we got to generate, and we can take one polarity of DC and we can convert it into a plus and minus. We have people all the time say, why do we need negative DC? Well, by George, if you didn't have negative DC, you wouldn't have audio. Right? You understand? So electronically, I can come up here and I might produce a plus 80 volts, and electronically, I might produce a minus 80 volts. And then what my stereo does, is it has two switching devices. We call them output transistors. And here's my stereo coming in right here. And when it goes positive, it turns this guy here off and turns this guy here on. Now it goes positive. When it goes negative, it turns this guy here off and turns that guy right on. And now I'm making AC. But I'm controlling the frequency, right? So you're listening to music. You got bass out there. You got treble. You got mid-range. And it's coming from DC. But what does it go into your speaker? AC. But you're controlling the electronics. So you're right. Alabama Power generates 60 cycles. But thank God I can take that 60 cycles and turn it into what? DC. Then now I got it in DC. What can I do with DC? I can't do it. I can electronically control that sucker. So my variable frequency drive, that's what it's doing. It's taking the 60 cycle coming in from Alabama Power. First thing it does is do what? Turns it into what? DC, right? Now they turn it into a nice big old plus and minus DC, right? And now what can they do? They can change, not only can they change the frequency, they can also electronically change the voltage. Perfect example is that dang function generator. I'm plugging that sucker into Alabama Power, and what can I do? Well, I can change the frequency anywhere I want to, and I can set the amplitude, because I'm generating that AC electron. So you're exactly right. So we got to run through a drive. If I run it off Alabama Power, it's going to run at 100. It's going to run at those regular speeds, right? You understand that? But if I run it through a drive, then what do? I control what? Okay. So what advantage does AC motors have over DC? If I can do all that with DC, why do I even use AC motors?
Cheaper.
They're so much cheaper, especially these induction motors. I mean, we're creating that center field by induction, so that's the big advantage. So for years, speed control was DC, until they finally could electronically not only change the frequency, but also change the voltage. As soon as we could do that, then now we go to AC drives. But we still have to speed control. We have what we call a drive, right? And then we have the motor. Well, we have that on DC. So if we have to have the drive anyway, I can take a DC drive to run a DC motor, or I can take an AC drive to run an AC motor. And so now what's dominating the speed control circuit? AC drives. I mean, they're putting out AC cranes now for years. Crane was DC for years. Now they're AC, because I can electronically not only control the what? The frequency, I can control the what? Voltage. They do it real neat. It's what we call pulse width modulation. It's the neatest thing you've ever seen. Where we send a bunch of pulses out and we change the pulse width, and then that big old inductor out there in the motor averages that out and makes it look just like pure AC. It has no. So if you looked at a variable frequency drive without a motor hooked up to it, if it lets you run it, probably it wouldn't. Very few devices let you, like solid state devices, don't want you to run these things unloaded. So don't ever run your power amp unloaded. If you've got a power amp, and it kicks off, then you need to go in and you need to figure out what's going on. Don't keep resetting it, because you're going to burn something up. So if your speaker leads, one of your speaker leads come out, we call it reflected power. Now that power's got to go somewhere. And what happens if it don't go into the load, it's going to reflect back into the amplifier and it's going to blow your output amp trim. So don't ever run a power amp unloaded. In fact, most of your car radios now, put out 30, 40 watts or 50 watts of power, and you can blow those things up. So if they keep cutting off, do it once and then try to figure out why. Don't keep resetting that thing, or you're going to do it. So we're going to hook this thing up. We're not, maybe not tonight, but before the end of the semester, we're going to hook up that variable frequency drive. We got one donated to us. We got a lot of them donated to us, but most of them that we have donated to us are 440 drives, and we don't have any 440 here. That right there is a 220 drive, 220 volt drive. It's back there on the table, that little blue unit back there on the table. That's a variable speed drive. And how do you program it? Most of it is just reading that dang nameplate. So you put the service factor in there. You put of course the hertz it's designed to run on. You put the speed, the maximum speed of the motor with slip, and you program that all into that thing, and they'll run these motors without any problem. They just can't go down to 0. So if I've got to take a motor all the way down to like 2 hertz or something like that, then odds are we're going to still use DC. So we're not doing away with DC drives. But if I can do 20 hertz and above, then most of these guys will work. In a lot of the applications, that's what we need. We don't need to go down all the way to 0. So how does a variable speed drive control an AC motor? It changes the what? Yeah, what it does is it sends out a series of pulses. And then what does it do? It changes the width of the pulses and the amplitude of the pulses. So if I change the width of the pulses, that would change the frequency. And of course, we change the amplitude of the pulses, and then we can, which is pretty neat. So yeah, if you looked at the output with a DC with a voltmeter, you'd see it start. You would actually see this voltage per hertz thing. You'd see not only does the frequency change, but also the watt, the voltage. All right, guys. Let's take a break and then we'll come back, and what we're going to do? Go to lab. What labs are we working on? So if you hadn't done the wiring up the motor lab, I don't know which one that is. MOC 2. So MOC 1 is the nameplate. That was due tonight. That's homework. Then MOC 2 is where you wire the voltage, or wire the motor. You wire it for high voltage, let me check it. You wire it for low, or that's backwards. You wire it for low voltage and check it. I check it to make sure you wire it right. Then you hook it up for high voltage, I check it. Then you rehook it for low voltage so we can run it, right? And then what do we do? Then after you finish that lab, what are you going to do to it next? You're going to do the reversing lab. And then after that, you're going to do the timer lab. There's one required timer lab. And then after that, as you get through those 2 labs, or those 3 labs, then what can you do? Go back and do whatever. And don't choose the most complicated. What do you need to do? Try to do the easy ones, right? And get because all these labs are worth 100 points. Whether they're hard or whether they're easy. And I just found out it's so much easier for me to grade that way. Instead of saying, well, this lab's worth 100 points. So what I would recommend to do is try to do the ones that are easy for you to learn. Alright? Alright guys, I'll take a break and come back and let's go lab. Somebody turn on all the lights for me.